Hi everybody, I'm really glad to see you. I'm Amirpasha from Research Center Jülich, working in Jülich Supercomputer Center. And today I want to talk about the possible application of Fair Digital Object for caching and automation. So I start with the most stereotypical things. I brought the description of reproducibility from Wikipedia, of course. And so the idea is we want to replicate an experiment, observation, or statistical analysis with a high degree of reliability. And then I borrow from a Fair Digital Object Forum, one of the working group, canonical workflow for research, some advantage of why reproducibility matter for us. So here I just collect some of them, like in a critical situation, we can reproduce our data when hard drive dropped in, I don't know, rain. And increased transparency, there is evidence that there is increase in the number of citation of the research that is reproducible, and also increase efficiency and productivity and help the continuity of science. But when we look at it, like how is reproducibility in research? So Nature carried out a little bit outdated reproducibility survey in 2016 and asked the research community that how is reproducibility? Do you see it works fine? Is it in crisis or not? And no wonder more than 80% of the researchers came back with significant or slightly in crisis. So it's pinpoint that, yeah, we have a hard time. I just saw that 38 should be 58, but yeah, you get the point. And as a person who works in geoscience and earth system modeling, so I was more interested in my own field. And what they reported is 60% of the community reported that they failed to reproduce someone else's works. And more frightening, 40% of the community reported they have trouble to reproducing their own results. So that's not the best place to start. And so, in case you're interested, I put a short link on this report from Nature. You can have a look. It's like 3 minutes on YouTube. But, okay. So that's the ground to start why reproducibility is important and why it's in crisis. If you had the privilege to see the Robert Kahn yesterday interview, he talked about digital object and pinpoint some strong features that for the context that I'm interested could be used. So it's identifiable by PID, it's support abstraction, support encapsulation, it's binding. They are features that is necessary, but I don't think is all we need for a complete reproducibility. So it's a place to start. And then we comes to why we gather here. So what is the next generation of digital objects? So fair digital object. It has some features that makes it much more interesting as a vehicle for complete reproducibility. We will have types and properties. We will have PIDs and the profiles, the attributes. If you had a chance to have listen to the talk from Peter yesterday about the works on distribution between mandatory and optional kernel attributes, which for us is interesting that to achieve the high degree of reproducibility that we want in the computational reproducibility sense. And for our specific use case that I will go in the next slide, which it's about versioning, as we work with lots of data that is continuously updated, changed, and modified. So the versioning makes it a bit more special. So with all this background, I just jump to our specific use case. Research Center Jülich Supercomputer Center, is hosting a TOR database, is the biggest tropospheric ozone air quality data. And we have more than 25 partners, and they're reporting on 2,000 different stations. And here's the name of some of them from German Environmental Agency, American Environmental Agency, Canada, European, lots of small firm. Then they provide us with the streams of data. And so it's very fragmented. And so we were interested to see how we can make a unified this. In addition to the raw data that we have, we also provide some statistical analysis. We also provide some aggregation. And so reproducibility is very interesting for us for the sense of first save time and the second save energy. We are supercomputer centers that actually use the energy of the small city of 30,000 people. So as less we compute, we will save energy, especially right now in the energy crisis time. But we have some problem. Imagine you are a weather station somewhere, and then 6 months later, after reporting your data, somebody visits like, there is a leaf inside the precipitation gauge. It was wrong. We should change it. And then they realize, this sensor was malfunctioning. They find out they need to recalibrate this data. So we have continuous streams of correction that comes after the data is published. So that's one part. The second part is we have continuous stream of new data. Suddenly the EPA announced like, they have new station here. So we have a gap in the middle of previous data that we want to fit in. So we have two challenges, and specifically for our case is the new data and modification of the old data. So when we are thinking about the caching and FDO, for the case of, a user, we produce some data, they communicate with our server, they get the data. When it comes to the second user, then we are not sure. Can we give them the same results? Did the underlying data change or not? So it makes it a little bit, we should trust the data that we have. But so what we came up with, so we can use a FDO as a vehicle for this reproducibility. So we suggested next to our server, we have a secondary server, which is housing our FDO. And the FDO combination of the pinpoint to the data and the metadata that specifically describe that sets of data and that snapshots of time and space, and wrapped with the version of the script and whatever the procedure that is carried out together, and we store it somewhere else. And when the second user comes, we just go and read the hashes. It's like, is it exactly the version that the user wants, or there is something's changed? So, or we can retrieve something from the past. And so that's the idea of that we are working now. And so here is like the schema of how the request works. Like you get a request, you go back and find all the time series that you have and check that if it exists, if there's exactly that what you want, you can retrieve it, or you put the compute request, just we go and calculate it, we come back. So from the compute part, it's the second part that we are interested also. As a supercomputer center, we have heavy loads of computation that comes. Lots of them are small. You can run it even because most of them are housed on VMs. So some of this computation carried out on spot. Some of them carried out on spot but takes longer time. So you need to wait and inform the client. Sometimes the computation is actually using HPC system. So we need to communicate this, go to HPC, queue, take times. 2 days later, the data comes out, you come back. So we find out FDO could be a nice vehicle to make an encapsulation of these computation. So then we use this as underlying workflows that communicate to the HPC system, come back. It's like small encapsulation of all we need. And so that's that next to it, we are actually already deployed a secondary server that is take care of our scheduling based on how big is the request, so it's communicate to the actual HPC system. So with that, I will come to the current status. So we're working currently on how to use hashing for identifying that specific FDO and how we use the specific encapsulation that exists, if it's that exactly what we want, because the problem is we cannot go and read megabytes and gigabytes of data and then come back as like, yeah, it's what you want, or no, it's not what you want. We should compute how we can make it as abstract and as fast as possible. The second part that we deployed is schedulers that can communicate with that communicate with Slurms, which is the underlying scheduler of the HPC system. And the third part, that is actually one of the reasons that these things happen, is the FDO the description of the data versioning that is interesting for us and attributes that we should find out for meeting our need. So with that, I will come to the end, and thank you for your attention.
And do we have any questions? If you could step up to the mic, yeah.
I think it's all. Yeah, it works. So my question is, how do you have a policy to decide when to produce a new version? Like, is it something that comes after each change, or you expect the data to be corrected up to a certain level to release a new version? And do you foresee to communicate these changes not only to the machines, but also to establish some sort of a subscription and notification systems to the human client outside, for instance? Thanks.
That's a really nice question, actually. Yes, actually, we do it in a both way. One is because we provide API. So there's API interface that they can actually check. There's also a website that provide the log changes, that if something happened, but we still don't have exactly policy like what is defined as a change. For us, any modification counts as change. Maybe in some point in the future we say, like, I don't know, 10% change doesn't matter, we can just neglect it, but very good point. Yeah.
Yeah, thanks. This kind of goes into the same direction. So when you've got your data set with a change and someone cites the data in a journal, so and you assign your PID to the, say, continuous data set, I'm not going to ensure that you cite the correct version in the end.
That's actually a really good question. That's the same as well. The idea is that we have this subversioning. So we have one word for the main roots of this data set that is published, and then you can pinpoint exactly what version that is being used. So when anything, you see some version of it in Zenodo as well, that you have a root PID for the data sets, and then you can pinpoint what version, including what changes.
My question is, are you actually keeping a copy of the whole data set, or is your FDO storing all the versions of the elements within your data set so that you are reconstructing the data set? So is it event-based, or is it kind of like a whole copy?
So far, it's actually a really good question again. Yes, so far we kept all this data, with all these versions, but the idea is we move forward. When we go with the concept of FDO, we don't keep all these data, and we just keep the version that is calculated, and then we rely on the archive of the provider for all the originals data. Yeah, we just keep the latest version with us.
And one final question: are you making the workflows fair digital objects themselves? So a description of the workflow, is that within there? I know that's very important. We had a talk on fair for research software, and that's an important component. But I think to really get to a fair environment, we need to describe the workflows in entirety, the dependencies, things along those lines that impact the workflow. So.
That is really true. Actually, we published our workflow as because when we published it with Canonical Workflow for Research Special Edition, which was, I think, April 2022, we introduced it how it can be a digital object. Still, there is no specific definition like how this fair digital object of this workflow looks like, but we published it like that's what we assume will be these attributes of the workflow itself. So yeah, that's really a point that we're going towards it, but it's also hanging on when the description is out. Sure. Yeah.
Okay, and then I think we're at time, so we'll move forward. Do we have Marisa?
Great. Good morning, everybody. My name is Marisa Conte. I'm here today from the University of Michigan Medical School, and I'm here to talk about work to develop linked metadata for fair digital objects that carry computable biomedical knowledge. So to begin, I would like to acknowledge my team. The name in bold, Alan Flynn, is the primary investigator on the work that I'm about to describe. Would also like to acknowledge the funding from the Department of Learning Health Sciences, where I work as a research specialist on our Knowledge Grid platform. I'm relatively new to this work. I have left my previous career 15 years as an academic health sciences librarian, so very familiar with FAIR in terms of research data management, and excited to be moving now into management of computable biomedical knowledge. So to start off, I would just like to orient everyone on what we're talking about when we talk about our knowledge objects that package computable biomedical knowledge, with the computable biomedical knowledge piece defined as an analytic or deliberative process that is machine actionable. So this version of the knowledge object should look pretty familiar to everyone from talks yesterday, but we contain the computable knowledge content within a bit sequence. Examples of computable knowledge could be something like a computable phenotype for classification for clinical research, a clinical decision support that might guide precision treatment selection based on characteristics of patients or groups of patients, or perhaps risk prediction models. This is bundled together with a deployment description, which is the runtime specifications. And in the first generation of the work to package knowledge objects, they had a service description that called up an activator over an open API. We also provide metadata, and as I'll discuss further, we're trying to move into more of a linked metadata environment, and then there's a persistent identifier, and most of the knowledge objects that have been produced to date use the ARC identification. So we've been really interested in the work to develop the FAIR Digital Object Framework. We are working, as I said, on linked metadata records, and what we're noticing is there is no linked metadata scheme for computable biomedical knowledge. We're hopeful that this will be under development with the formation of a community that kicked off in 2017 called the Mobilizing Computable Biomedical Knowledge Community, or MCBK for short. This is an international group that is composed of representation from academia, from industry, from government, and exciting for me personally, also patient advocates. And the goal of the group is to really mobilize computable biomedical knowledge into more general use, but also make sure that this is done in accordance with the FAIR principles. So one of the work groups of the MCBK community is focused on technical standards and infrastructures. And in 2021, a work group of this working group published a paper that identified 13 categories of metadata for computable biomedical knowledge. We went through a process where we did an environmental scan of existing literature, came to consensus on the categories, and then also were able to identify for each of the categories published papers that represented at least one of those categories. And what I would like to do is spend some time talking about the 6 categories here that have the little asterisk next to them, because we think that these may be somewhat unique for computable biomedical knowledge as compared to identification, location, preservation, some of the things that might be more general. So with knowledge domain, we're looking to describe the relevant biomedical domain or topics. And for linked data, we would like this to be standardized. So some of these sources that are identified are the Unified Medical Language System, or UMLS, which contains the medical subject headings or mesh headings. There's also a standardized nomenclature of medicine that contains a large number of terms and classes. Purpose would describe, or in some cases circumscribe, the intended use of the computable biomedical knowledge object. So for describes, I'm talking about things like you can say that something is used for clinical decision support. With circumscribed, you might want to identify a population for which that's not relevant. So for example, maybe some knowledge objects are relevant for adult patients but wouldn't be useful in pediatric populations, and you could use purpose to indicate that. We know that the relationships between knowledge objects are going to be really important, and we've discovered that there's really no way to describe these in standardized terms. And some of the relationships that we might want to describe would be sequential relationships. So if you have a treatment, you have to have a diagnosis that comes before the treatment. Dependencies, and then comparisons, which are useful in comparative research. Technical metadata includes the information that's necessary to deploy, integrate, run, or use computable biomedical knowledge. And then these last two categories are actually a bit outside of the FAIR framework, but they talk about things that can help to establish trust, which is particularly important when you're dealing with biomedical knowledge and has been something that our patient advocate partners have brought up. So one of these is the evidential basis that describes the data on which the CBK is based, how that data were obtained, and then the strength of the evidence. We're also interested in evidence from the use of the computable biomedical knowledge object itself. So this would include evidence that emerges as the CBK is used, either in practice or in research. And again, methods of obtaining and analyzing data and the strength of evidence. And we do have some ways to link back out, for example, to organizations who establish these ways to rate evidence quality, including the US Preventative Task Force. So what we're doing with this in our current practice is moving from what is a really basic metadata record that we started with our knowledge objects. So this is a knowledge object that represents ongoing work with the Canadian Centre for Addiction and Mental Health, and they're looking to move the use of a specific score interpreter that scores depression into something where the function can be represented as a knowledge graph. So the metadata that was in the first generation of this used as its context the knowledge object integration ontology. And it's pretty basic. So you have an identifier, you have the type, which again refers back to the COYO knowledge object, a couple of keywords, and then pointers to the service specification, deployment specification, and payload that are all contained within the knowledge object. And what we're moving towards is making this much more robust metadata and making it linked data. So the what's used here are DC Dublin core. We also still use the COYO ontology, and then the functional knowledge ontology are all represented here. So this is a prototype for the work that's being done to move this particular knowledge object into a knowledge graph. If you plug this into the JSON LD playground, you can see that it's represented as a knowledge graph. And in summary, we're working to understand how computable biomedical knowledge objects can be represented and used as a class of fair knowledge objects. Beginning to see that a linked metadata schema might be specific to some of these classes, and definitely that additional terminologies may need to be developed. So for a lot of the specific asterisked categories that I pointed out, there just aren't formal representations or terminologies within those areas. Also, because we anticipate that a lot of these metadata records will be quite large, it seems that automating some of these will become important. And with that, I'm happy to answer questions as I can. Thank you for your attention.
So very nice work, thank you. Identifying 13 classes of metadata, do you think that if we look at all the fields of science, that we will be able to find similar categories in other fields, maybe named slightly differently, but using the same strategy? And could we standardize more on that, generalize instead of trying to specialize?
Yep, I think that that's a great point. Thank you for that observation. Yes, I do think that a lot of these, although we've identified them within that paper as being suggested that they are specific to computable biomedical knowledge, I think a bit of that was also around the community building. So the social aspect of infrastructure is oftentimes more difficult and potentially more important than the technical elements of infrastructure. So I think that having these community-defined understandings of what we would want to have represented as computable biomedical knowledge is important. The ones that stand out to me as there potentially not being a lot of overlap might be the ones that deal a little bit more with trust. So maybe the evidence basis and then the evidence basis for use of the knowledge object within practice, that might be a bit different to other disciplines, but having spent 15 years or so firmly grounded in biomedicine, I'm certainly not an expert on other disciplines, so that's also open to discussion. Thank you.
Thank you, Bob, for asking half my question already. So I wanted to build on that because of all the existing metadata schemas, right? So because we already talked about typing of FDOs and so on. And what are your thoughts on how we should do that kind of mapping? Do we just use these as they are, or do we need to have some kind of proxy types for these? Do we need lots of different types of FDOs at the same time as we have different metadata schemas, or are they just the one and the same thing?
Great, thank you for that. I think, again, one thing that was important for us as we started work on this paper, which began, I think, in 2019, we're still a very young community in terms of mobilizing computable biomedical knowledge, so being able to define specific types and think about what might need to be represented to make those types implementable, reusable, trustable within certain use cases was important. I think that to some extent, you probably aren't going to stop communities from wanting to differentiate themselves, especially as it leads to deeper understanding of their own artifacts. But as things become more linked and more interoperable, maybe some of that will start to fade.
Thank you for your talk. I had a question. You mentioned that there was a potential to automate some of the process of the linked metadata generation. What strategies are you exploring for that, and over what volume of data are you working?
So what I should have said if I didn't was that we're very much hoping that automation will come to be a part of this, because again, there's a massive amount. If you start to look at linking out to all the different places that you might want to include information about. So I think the kind of weasel words on the slide were, we think this might be important, and hopefully somebody is going to be doing some work to automate. Yeah, right now we have just under, I think we're at about 80 knowledge objects total, so the total volume that we're working with is not large.
Okay, thank you.
Yep.
We have time for one more.
Hi, very interesting work. This work comes mainly from the learning health systems community, and it's been going for quite a long time. And the learning health systems community has a significant interest in privacy preservation. And we heard yesterday from Bob to say, don't touch the whole notion of sensitive data. Could you make some remarks about how your need to be able to handle sensitive data would relate to influencing fair digital objects in this world?
Interesting question. I'll try. So my home department actually is the Department of Learning Health Sciences at the University of Michigan, which houses a journal in learning health systems. So there is a lot of conversation around these different things. The objects here as they're being discussed are separate from the data themselves. So when you're interacting with a knowledge object, you're not actually interacting directly with data from any particular source. Our hope is that these knowledge objects can be used not only by learning communities that are working with specific data sets drawn from electronic health records, in which case, in the United States at least, if it's research not linked to quality, that would have to go through an institutional review board and everything would have to be approved. Other use cases for these can be in large clinical data research networks, which can be either networks of networks, like the Outcomes Research Network in the United States, or even international, like Odyssey, which is observational data. I had something brilliant to say and just lost my point as I was trying to remember what Odyssey stood for. But I think in general, the objects themselves aren't containing data. What we would like to do with a couple of types of objects, computable phenotypes in particular, is to be able to package and deliver these with synthetic data sets so that people could actually use them in their own environments to see which of many phenotypes might classify their patients best. But again, that would be purely synthetic data, so privacy wouldn't be of a concern. Okay. Thank you.
Thank you, Marisa. Okay, and then we have Jan. Okay. And we're right on time, so this is working out perfectly. I've never heard something that's been this close to on time each session.
Yeah, welcome everybody to my talk. I'm talking about the implementation of a photovoltaic system model using fair digital objects. I'm Schweikert from Karlsruhe Institute of Technology, and yeah, let's start. So the motivation why we did this is we got a new PV system on the rooftop of our institute's building, and we want to use this data in scientific workflows and simulations. And also we want to make life a bit easier for our operational staff, so that they can find all their the data about the facility in one place. And so we sat down and thought about what data needs to be described and stored to capture the whole system digitally. And we have three, let's say, categories of data. One is the structural composition data, which states which components exist in the system and how these components are interconnected. Therefore, we're using in-house developed ontology, the PV ontology. Then we have the data sheet and positional information. Data sheet information is mostly the master data of a component, like, for example, by the power inverter has a maximum power output or a maximum input voltage level, stuff like that. Positional information is geo-coordinates and the dimensions of the housing of the components, and we are using for all of this data IC61850, GeoJSON, and SensorML. And we are also using SensorML for the measurement data to describe the structure of the captured data, as well as the location where this data is stored. Yeah, and what we end up is we are using 4 different incompatible standards. So we get a bunch of objects that are unrelated to each other. And the question is how to make clear which information is about what component. And therefore we thought it's required to create a coherent object graph where all the information is related in. And yeah, we are using fair digital objects for that, but we have 2 requirements, prerequisites to this fair digital object. So first thing, if we need fragment identifiers. So fragment identifiers you may know from HTTPS. It's the part with a hashtag in the URL. So in the big text document, you can give a paragraph an ID, and if you add this ID as a hashtag to the URL, the browser jumps directly to this paragraph. And the same idea shall be applied to fair digital objects, so we can add a fragment identifier to a reference to of a FDO, and then I can reference specific entities inside of the data of the FDO. The second requirement is that we're using the Helmholtz kernel information profile. So the kernel information profile you may know from the talk of Rainer earlier this morning. It's defined by a working group of the Helmholtz Metadata collaboration where I'm part of. And it's basically an attempt to a first unified Helmholtz-wide kernel information profile. And it's based, of course, on the RDR recommendations. And the 2 important fields in there which I'm using for the concept is has metadata and is metadata for. These 2 fields allow to interconnect FDOs with each other. So with has metadata, I can state, FDO can state that another FDO contains metadata or additional data to this FDO. And yeah, the is metadata for is the reverse edge of that. And now we have both requirements. We can come to the concept. So we see up here. Okay, you don't see the dot. So the big blue rectangle above here is the instance ontology graph, or the ontology instance graph. And down there we have 2 example data objects, which are about the inverter. So the IEC data about the inverter and the GeoJSON about the inverter. And the question is now, how can we connect the node in the instance graph with its data objects? And the first thing we are doing is creating an FDO, FDO449. This FDO references the whole ontology instance graph. After that, we create another FDO, the FDO4711. This is, we call it a bridge FDO because it uses this fragment identifiers to reference data inside of something. And in this case, it references the FDO449, and with the fragment identifier part, it references the node in the ontology instance graph. Then we can create another FDO, the FDO129, which is the FDO for the IEC data part. And now the only connection that is missing is the connection between 4711 and 129. And we're doing this with the has metadata path. And now we have a field. And now we have a path between the inverter and its corresponding data object. The same we can apply for the GeoJSON object. So we create another FDO connected with the has metadata, and now both data objects about the inverter component are in the graph. And to create the coherent graph with a single root entry node, we can create another FDO, the FDO2022, and this FDO references with the has metadata all bridging FDOs, as well as the graph description FDO. And also we can use optionally the digital object location with the fragment identifier to reference the root node in the ontology instance graph. For concept, maybe something I'm missing. Advantage of this concept is it's totally agnostic about the use standards. The only requirement is that I can reference somehow data inside an FDO with a fragment identifier. So we could easily replace the IEC standard or the GeoJSON standard by other standards if they better fit our modeling. For concept verification, we thought about creating a little application which allows us to render the whole PV system as a diagram, and the user can explore all the data about this system by clicking through the components. Also, we have a little mask where we can type in the PID, and to show that with the concept the whole graph is traversable, so you can put in the PID of the root node, and you get the rendering, well, all the data about the photovoltaic system. If you only type in the PID of a bridge FDO, you get only the data of the component, and the same for if you only type in the PID of a data object, then you only get the rendering of this specific FDO. For the implementation, we're using at the moment the meter store, developed by the colleagues from the Steinbruch Center of Computing at KIT, which stores our data. We have a custom PID resolver system at the moment. This means our PIDs are not globally routable at the moment, but we will change this soon. For the front end, we did a web application using TypeScript and React, and the idea of the application was we have in the top view a table which allows to display the content of the FDO, so the data that's directly attached to the record. And in the down we have a plugin mechanism which loads which displays the data based on the data type of this FDO. Also, we needed to create some data types. We're using the GWDG data type registry test instance in Göttingen. And we created two, let's say, types of PIDs. We have data types. We have data types for physical entities, which said I'm a physical entity like a photovoltaic system. And we have data types registered for standards, for example, which state this FDO is using 61850 in the file format JSON. Now some screenshots of an early alpha of this. This is the whole rendering of the page. So we have in the top the information about the FDO record, and down there we see the rendering of the whole system. And if we click now, for example, on one of the orange rectangles here, these are the measurement devices in this rendering. We get the data of the measurement devices displayed as a graph. In this case, it's the battery power and voltage of the last 6 hours of this of the PV system. Some remarks on the implementation. So, what's really important is that we model all edges, so the forward edges will have metadata and the reverse edges with is metadata 4. Else we are not able to traverse the whole graph from each node. And the second remark is we registered this data type for IEC 61850 with state it's this standard, and we the file format is JSON. But the standard contains more than 250 classes, and it's not clear from the data type alone which class is used in this specific FDO. So the problem I'm ending up with is this animation. So I'm loading the right plugin, and the plugin is giving me some views. And now I need to click through the views to find the correct class. And this time, in this case, it's the photovoltaic module. And the only solution we came up, or how we can circumvent this, is to use to let the data object itself state what kind of class it is. Yeah, that's everything for me. Thanks for your attention. Do you have questions?
Very interesting, and I appreciate you mentioning what you used to implement the FDOs. Can you elaborate on what you felt is lacking in existing technologies that need to be addressed by future FDO standards and technologies? What is it that you wish you had that you didn't have?
So one thing what was hard is if you're working with FDOs at the moment, you do not have a clear guidance. So you do something, you do not know if it's right or wrong because nothing is defined that hard. So for example, data types is a big playground. You can try stuff and you only see if it's working, if it works, but you don't know if this is the same way others would do this and if this way will still be valid in future. Other stuff is a lot of software is missing. So handling the resolving of the PIDs, and in this scenario we really need to resolve a lot of PIDs because every object has at least 2 or 5 other FDOs connected to each other. So we need to request, gather the data, analyze the data, and then do something with the data. Yeah, there should be some libraries which take off this overhead for the programmer.
So that's a bit of the curse of an early adopter, is that you're not sure if you're doing things right.
Yes.
Somewhat trailblazing, but it's important work. So let me ask, initially you had an environmental box with several components in it. You described the one component. It's not necessary to, and I'm not using the microphone, to describe those other components. Are they in the kind of the large box description? Are they static enough that you don't need FDOs for each of the individual components? So you had 4 objects in the large blue box.
Yeah.
And you only really described one of them, and then the standard.
Oh, okay, yeah.
So do the other components just not need description, or are they static enough that they...
This is up to the developer. So this is just the example for the inverter, but of course we need to do the same for every other component where we have data of. Mm-hmm. And yeah, the ontology or the graph is only describing the whole system as a connected graph, and the data is provided externally. Mm-hmm. And then the question is always, what data do you have from which component, and if you need to store it, then you need to apply it with this concept.
Very good, thank you. Other questions?
Good.
Okay, thank you very much. And I think, Dan, you're next.
Let me take the microphone. I tend to wander a bit. Let me see. So, yeah, hello. I'm Daan Broeder. I'm affiliated with Clarin Erik, and Clarin is the research infrastructure for language resources. I'm going to speak about towards fair access to data. Yeah, the background. So this presentation is about what making thoughts, experiences within the Clarin infrastructure, but also within SHOC, which is the European Thematic Cluster Project for the Social Sciences and Humanities. From the title, Towards Fair Access to Data, you can already see that we think we're not there yet, because although there was lots of success with raising awareness about FAIR principles and open science, and also there is considerable progress with respect to instruments for discovery. There are very many catalogs around, general ones, thematic ones, too many, I would say. You need to guide the user to which discovery instrument to use, but that's not the problem. There are also data citation becoming more and more en vogue, with offer references to resources hosted in repositories. However, all those catalogs and data citations do not guarantee access to the data itself. From the catalog and from the citation, you mostly get a pointer, a PID or a URL pointing to a landing page that describes the resource with human readable instructions how to access the resource, if you're lucky. These pages are difficult to parse and so unusable for large-scale data processing and verification. In all, not at all machine actionable. Why this setup then? It comes with the standard repository systems. They offer a editable landing page, but there is no systematics about how to, let's say, specify the link to the data resource itself. And it's also very easy. These landing pages are editable. So it's easy to say, hey, this version was just updated. You can simply type it in. And also it allows, and maybe that's the more important reason, it allows proper human readable branding and acknowledgement of the stakeholders. That's why the repository system organizations like it, I think. But anyway, so machine actionable to get from the URI to the landing page, but from the landing page to the data, not machine actionable. Okay, in the context of the Clarin PID task force, which is not only about PIDs, but also about access to data, we have been thinking a bit, brainstorming a bit about what are strategies, what are technical solutions to improve that. There are 4 mentioned here, which I will go into in more detail. This is by no means an exhaustive list. It's just what we know is around and where we have some experience, not first-hand, but second or third-hand, about their use. First, signposting. So the idea is that you need to get information about where to find the data, not from the landing page, but from other information sources. Now, signposting is one such technology. It provides general additional technical and biographical information. There are 2 options there. You can either embed the information in the landing page itself, that of course assumes that it's HTML, or, and that's I think the better way, you can transfer that information through use of HTTP link headers. Advantage there is that you don't have to download the resource first. So the resource also is not obligatory an HTML page, can be everything. And you don't need to parse the resource. But there are size limitations for the HTTP link header size. They're not officially standardized. I think it's implementation dependent on what can be the maximum size there. But anyway, it's nice. It's being used, but I don't. It seems somehow to have stalled as a technology. We don't see any big increase in its actual use. Another solution is homemade, what we call the Clarin Digital Object Gateway, the DOG, and that's a solution where we embed knowledge about every individual Clarin Center's repository system in the DOG. So there is a small database that tells, well, if you find a landing page here, you can parse it, but you have to parse it in this and this way to get the actual link to the data. Now, that's of course not really scalable, but it's doable in an environment where you have, as Clarin does, less than 30 Clarin centers. Clarin is not the only research infrastructure to use this strategy. There are more, but I cannot name them now. Another solution is the PID kernel information. The PID record allows you to also store other type of information than just the link to the landing page. So a link to the data can also be administrated in the handle record. I know of individual organizations and some infrastructures that have experimented with this. So if you look at their handle record, you will see next to the URI for the landing page also URI for the data. There is not much against its approach, but you need, of course, strong discipline in maintaining this additional information. But you need also strong discipline with the previous one, because here too with signposting you need to maintain a database with that, an extra database with that information. Yeah, but anyway, this will work. Then of course there are the fair digital objects, which we have not implemented. We don't think there is yet a critical mass of implementation that shows the ways. We could experiment, of course, but we prefer to wait. Anyway, fair digital objects allow you to encapsulate the object by what we call a rich set of FDO attributes. There are ways of linking directly community services or general services to the different attributes, or you could find suitable processing services by typing. Both are, I think, excellent, but via a few proposed attributes, such as, for instance, the digital object location, and I think a previous speaker also had that in his slides, and the access method description, machines can find out where is the data. Not only giving a URI, but the access method description also gives you the possibility to specify an API, right? And if you look at this picture, and this is what I call the handle system binding of the FDOs. FDOs are supposed to be technological agnostic, but well, there are not so many choices to be made there. This looks a bit like an extension of the previous solution. Here you have only 2 attributes, and here you have a rich set of attributes which can convey, of course, more information. Now, what to do? For our immediate needs, we need short-term solutions, but also we don't want to invest too much in and get locked up in badly scaling technology. So for us, the choice would be to combine the dog with signposting. Signposting is a bit more general, so if you want to use it not only for the Clarion centers but also for related centers, you can gamble that they have signposting going on. Easy to test if there are linked headers in your HTTP response. If so, you're lucky. If not, well, you can find the dog. You can try out the dog. Long term, of course, it's not scalable, and there we see advantages with the general scalable and protocol independent. I should have put this between quotes, FDO approach. Hybrid solutions are, of course, conceivable. I can see possibilities having what I call FDO proxies between the FDO machinery and data hosted by signposting compliant repositories. I think this is my last slide. So. Questions? It's long enough.
Please correct me if I got it wrong, but as far as I understood, you were assuming that the data is located at some URL and you could retrieve it in principle by HTTP. So what about data that is on tape, so, that you would need to stage to disk before you could access them via HTTP?
I think there are legion implementations where URIs trigger certain processes in the repository systems that take care of the staging of the data before it gets accessed.
But in the meantime, each HTTP query will time out.
That's a problem with those. That's true. But there are ways of translating URIs, of course, to some logic that does some things.
It's some sort of scheduler.
Yeah. Okay. So maybe you get
To tell the client how to schedule it.
I think there is even a special HTTP response for that, and then you can of course decide to come back later. But it's not ideal. No. And FDOs there also offer a better solution because you have the access method that can, let's say, deal with that delay.
Hi, so I'm happy to see the fair signposting used as a kind of stepping stone here. I just want to point out that it can be scalable as well because you can have the link set as a separate resource.
I'm not saying in any way that signposting is not scalable.
Yeah,
God
exactly.
forbid,
Yeah.
No.
But I wanted to ask, because it touches on what you also said about the handle kernel data, right? Because you have kind of a duplication there, right? And as well, you could have the same issue of scalability in the handle system's attributes, and that is restricted how much you should put in there for...
Every technology has its limitations.
Yeah. But isn't that something we should come with strong guidance on how you should structure it so that when you resolve, you know where to look? Because if, again, we're building a system where you need to have a heuristics of trying 6 different places, if we define that in advance, then that should help to get it predictable.
But this should be steered by experience, I think. In different environments, you would need different, how do you say, priorities in trying out things. And for Clarin it would be this, and for other environments it would be something else. Yeah.
Thank you. I think we're at time. So, and Sharif.
No, this is good. Okay, cool. Okay, thank you everyone for joining us. My name is Sharif. I'm from Naturalis, and I'm also part of the Disco project with my colleagues here. So I will primarily be talking about Disco. However, I also want to make this point about data pipelines. So we're all used to data flows, databases, and then moving into sort of this fair digital ecosystem towards the infrastructure. So I will be emphasizing that point, but however, I also want to talk a little bit how we're thinking about this design within Disco. So what is Disco is currently is a project. So we are a European funded project. However, we will be a research infrastructure soon. So what we're trying to do is combine all the natural science collections data. So museums like Naturalis, botanical gardens, and other research collections. And you can see lots of national facilities and countries are involved. And we're trying to create sort of a more integrated infrastructure approach to all of these physical objects. And the physical objects are basically enormous sources of data for researchers, not for biologists, but also genomics and other applications as well. And just to give you a few numbers, what we have currently are billions of objects around lots of institutions in Europe and of course the rest of the world as well. And not all of these are digitized, so there is a coordinated digitized effort as well. And digitization not just means just getting a picture. There's a lot of different, types of digitization involved. We have insects to dinosaur bones to small things. So a variety of digitization approach. And of course, it will generate data. And then, of course, the usage of this data is also going to change the way we're doing now. So from that, we're trying to argue to move into a more fair, digital object infrastructure-oriented approach. And this is where sort of the ideas behind Disco coming in. And this paper that we published, this is sort of a pre-FDO forum thinking, mostly coming from the RDO, sort of explains some of the thinking over the years, how our community is evolving. Of course, some of the digital applications are not new within our community, but thinking about fair and fair digital object
is sort of evolving, and you can look at that paper as well. Okay, I have a short video, and you'll see the example, the point of this video in a minute. Let's see if it works. So just to give you background, this is a very famous car ad from 1964. No. Anyway, I can just describe what the video was when the video is not there. Anyway, so if you go to YouTube and look for Volkswagen 1964 car ad, so what happens is that this guy, it's there's a snow happening, it's the middle of the night, there's a little car coming in, and then after a few seconds, the voiceover asks it, have you ever wondered the guy who drives the snowplow gets to the snowplow? And there's a dramatic pause. And then, of course, the answer is, he drives a Volkswagen to go to the snowplow and gets the snowplow. Anyway, so the point is, let's see. Okay, so we know the answer, how do we get to the snowplow with this little car? But have you ever wondered how all the data from the data pipelines goes to the, big infrastructures? Of course, the answer is FDO, but we'll get to that later. So the interesting thing about when we start thinking about database to the infrastructure level, there's big complication starts to happening. You have the global, the local, the policy, and the social. And there's a lot of study done, sort of the infrastructure studies, especially from Jeffrey Bowker and others. So they've been trying to think about all of these things in a much more coherent way, starting from, of course, from the database and the records to go onto this higher level. So that's the question I think FDO Forum is also interesting to address, even though FDO Forum is not about the infrastructure, but these components, the digital object, will help us to build that infrastructure. So this is also very core into our design thinking, what we have in Disco. As I mentioned, all these physical objects, researchers need to physically look at. They have digital things, people are moving around, things are moving around. And there's lots of progress happening in this domain. However, we want to get to the integrated model with better access, better insight, and optimizing some of these operations. And as I mentioned, we're still in the preparation phase, but we're doing a lot of things with prototyping and demoing with fair digital objects. So hopefully in a year or so, we will see more of this coming in. I'm not going to walk you through the whole thing, but just to give you an example, like from records to database, there's a whole set of things that we have to deal with. So on this corner, we have what we call the collection management system. So these are the records of the physical objects we have in our museums and other organizations. Of course, there's data aggregators that publishes these things. But there's a whole sort of activity going on to get them into the level where we actually work with them. Of course, we have digitization facilities. These are machines that creates these images. There's ontology standards, existing standards, new standards. And then, of course, we enrich these things. And all these little boxes are your data life cycles. Even though here you can see as a layer, think of it as more of a data life cycle that's happening. So FDO, as you can see on the digital, what we call the digital specimen, which has a very concrete link with the physical objects, is a very core component. But there's lots of other things that are happening. Probably FDO will help, but not in everything. I mean, there's policy involved and other orchestration and infrastructure as well. So this gives you an idea. From this corner of this little database and aggregator, we need to sort of build all of these things. So here again, our physical specimen, which is again the records in the museum, but we want to get to this other side, make them fair, actionable knowledge unit to have them, operate as fair digital object, part of the bigger infrastructure. And this is Sabina Leonelli. She was also in an event organized by the Fair Digital Object Forum a few months ago, talks about these things. And this is also ties nicely with the car analogy. So we have records, these small facts in the databases. I mean, we are all familiar with that. We need them because this is how we organize. And these are easy to use nowadays. You can import, export, send it. However, the small facts are connected with big facts. That's where all the big problems and things we need to solve. But we need a vehicle to get there. And that's our, FDO could be that vehicle to get to the snowplow. Another example recently I found was very interesting. Some of you might be familiar with this model organism research. The research is fairly old. This database was very popular around 1990s. Model organism is basically sort of, this type of fly is used to answer a lot of biological questions. Very popular database. But if you go to now flybase.org, you see this. I mean, the National Human Genome Research Initiative basically, cut down their funding, and they're basically asking for money to support this. So again, these are records in a database, very important. We have these small facts, but if we treat them as a database and records instead of sort of this higher ecosystem and infrastructure, we end up in this kind of situation. So it's common in lots of other domains, so it's not just this domain. So what we're again trying to do is think about the existing policies and existing infrastructure and how we can get to that fair digital object world. And for us, is the specimens and objects that are connecting all these workflows and data classes. And we talked a lot about the persistent identifiers, and that's going to be very important. And other talks you also have seen, the PID records and things will be persistently identifying these digital records on the digital domain. And of course, we have all the physical identifiers in the database as well that we need to keep track of. And when we started thinking about these things, we realized that this is a huge global effort. Of course, DISCO is a European effort, but we started reaching out to our colleagues in the US, in Australia, and other parts of the world. And this paper was an outcome of some of this global consultation, and fair digital object idea is very core to this concept of digital object, digital extended specimen. The idea is basically, as a researcher, when you collect objects, you also want to think about all these links. And again, when you store data, you have those links as well in a much more actionable format. So you can see here, there's a core PID, and then all the metadata and external information that's attached to that digital specimen. And we wanted this to be much more dynamic environment where you have the core physical specimen static, but in the dynamic world, you can build more relationships and add more things to it. So now I'm gonna give you a few examples of some of the service and operational we're thinking about with DISCO and other organization. And one is basically what we call specimen data refinery, or the process. So a lot of these specimens, when we digitize, comes with very minimal data. Even though it might have an image or a picture, it needs a lot of annotation and extra work. For example, it might have a handwritten note or a lot of things in the labels of the specimen that needs basically extraction and then adding annotation or extra information. So we are working with the Synthesis project and also with people from University of Manchester and Elixir. Stian and Carol is here, they will talk about that a lot. Basically, it's an orchestration framework where our new data model, what we call the open digital specimen, will get into this workflow, and then different tools will come in, and then you will have AeroCrate as a model of fair digital object that will encapsulate some of these things, and you'll have an enriched data going back to the original digital specimen. So there's a lot of experimentation going on. This paper talks about that, and also the canonical workflow is also mentioned there. So for example, one of the things that you could also do in this kind of environment, you can plug in different things. So we have very specific machine learning needs for image analysis. For example, here we need to know, measurement of a leaf or flower or things like that. So they're very specific, domain-specific algorithm that needs to be plugged in. So this environment and also this environment helps us to bring all of this together. I mean, this could be a third-party tool that another researcher is working on, but very important for herbarium sheets. It might not work on insects or other things, but these are the components that would be nicely plugged in. And of course, the idea is that we want to capture this thing in fair digital object with an identifier and persistent metadata. Another project we just started, DISCO and other organization, is another big thing called biodiversity digital twin. And the whole idea behind digital twin, it's a kind of a buzzword, but idea is to sort of simulate the physical realities in a much more actionable way. And this is sort of a very simple idea of thinking about what are the parameters that we need to know to, sort of simulate and make the digital twin as real as possible. And industry has done that, medical field has done that, so in biodiversity is fairly new. And as you can imagine, the complexity, how do we describe our environment in this fashion? So been working with a lot of different people in this. It's a huge consortium, and fair digital object will have a big component here. And one of the deliverable we have to produce after end of this project is a interoperability layer with very different research infrastructures that are dealing with ecological model, biodiversity, species occurrence data, monitoring data, and of course the data coming from the museums as well. And supercomputer in Finland, they're leading in this project, and they will be a core component of this. And I'm also interested in what Amirpasha talked about earlier. It has some nice, interesting overlap to, so it'll be interesting to talk to you later as well. Basically, we're thinking about the same thing, how this fair digital object could be part of that encapsulation, and then however we envision these digital twins could be part of that ecosystem. And of course, we need quality indicators, because most of the current fair data indicators are very data set based. So if you don't have a particular type of data set or metadata, it doesn't allow those metrics. So we need to also think about how in this environment we have. And again, there's a big focus on the workflow hub, Crate in this as well, because we have ecologists, we have climate science data, and other people coming in with all sorts of different workflows. And also different people understand workflow differently, so we need to reconcile that as well. So yeah, check that out, and there's a lot of webinars that already happened from this project, so that give you an idea of some of the use cases we're trying to address in this digital twin project. Just quickly to show what exactly digital object in Disco will look like. Very similar to some of the examples you showed before. So here, this is an annotation done on a digital object. So for us, annotation is basically somebody goes on a database and looks at a particular element in that record and say something about it. So for example, here, this was a automated annotation done on the date, event date of that collection object. It basically says that it does not have it, and it fails a data quality check. But the important thing is that each annotation object has a PID, and you can also look at the PID record, similar to what Dan was showing earlier, so this kernel information, and it's tied to the target, so we're using a W3C annotation model to connect these two. So basically a close connection with two different type of digital objects and describing the annotation. And we're still in the early process of figuring out who gets to do an annotation, what happens, machine versus human and things like that. So again, this is the digital specimen object where it has more information about what type of specimen is it, who owns it, and other things like that. And this, the other one, basically connects that with the specimen object. So anyway, so these are the sort of the core component we're thinking about. But again, remember, the infrastructure is sort of our goal to build all of this thing. So thank you again, and you can find more information in our GitHub and blog, and we also have active Twitter and GitHub space, so please follow along. Thank you.
Thank you. And we have time for questions.
I can do one.
Oh, yeah.
Okay. I mean, I should probably know this is I'm also in the BioDT project, but I'm thinking, because you didn't get to cover that much, but we have there lots of these models, computational models that simulate systems and so on. And I wonder, what is your take on persistent identifiers and archiving in this respect, particularly considering you need powerful supercomputers to run some of these simulations and so on. How does that connect to longevity, archiving, and preservation aspects of fair digital objects?
No, thank you. That's a very good point, and it's also one of the things we have to work on in this digital twin project. So I think a lot of these boils down to best practices and policy, and I think that's also the question you ask about, if I have to wait for the loading of the tape and things like that. So I think one way I'm thinking about is that we already have a lot of best practices, within our community. It might not be sort of part of the HPC and supercomputing environment, but we can actually learn from some of these practices and then somehow bring the HPC community and our community sort of in the middle to see where we can bridge the gap. So especially from the sort of the pure biodiversity science aspect, the HPC is fairly new component, even though we do a lot of large data processing, but not in the scale that you would do for in climate study or astronomy. And then I think what we can also provide to that community is that we have done a lot of things with data standard and community's practice within our community, and there might be some gap that in the HPC community that's not done. So I think that's fairly, I think non-technical way to start, but I think that will give us the ground to better have the technical solution when we get together. So to me, it's primarily sort of more of a social and political problem, and then we can figure out the technical things. Yeah.
So I saw there you had Galaxy tools on one of your slides.
Yes.
Have you done any integration with FDOs into a Galaxy environment?
Yeah, that's what he's doing. Yeah. So it's a collaborative project with them and Disco, so he can.
Yeah, so we in Manchester are the ones working on the Galaxy side of it, and we are kind of not quite there. And as part, you can come see the poster in lunchtime, because part of the challenges we had was that we are passing FDOs between things in the Galaxy workflow, but it's a kind of like a local digital object that is not published, it's not got a handle and so on. And so you have this progression going on as the workflow is running. But then you need to kind of finalize and deposit it in the end. And so that's the level of tooling we're working on. And also combining with our crate so that we can add the provenance of the workflow run at the same time. Because now we have the history of how all these digital objects came to be. Because we're also doing large-scale workflows. We're running many thousands of digital specimens through the same workflow in Galaxy.
Yeah, so one of the things, like when that project started, we didn't have a robust handle infrastructure in the Disco side. So that's why at the moment they're not using that. So one thing we will do in the next few months is basically that workflow somehow talk to our Disco handle server and create those PIDs and it will be more, FDO like, yeah.
So I've been on a few fair proposals with the Galaxy team, and I'm wondering if it's time to bring in fair DOs.
Yeah.
So that's at the level of the development team for Galaxy. So very good. And I'll come see your poster. Okay. We have one more talk, and it is Karsten.
All right, so this is my standard phrase. Actually, I'm the last one between you and lunch, so that's kind of, I'll make it interesting. So I'll take a Daan's approach and take the mic. All right, what happened now? There we are. So this is actually very interesting because I can actually pick on many things which were, or actually pick up on things which were just mentioned. So this is actually falling good together. So actually I'm Karsten from the German Climate Computing Center. What we do is we provide the German Climate Computing, or the German Climate Science community with infrastructure, HPC, disk archive, all these kind of things. And we are in data management. So what we are here, so I don't think I have to tell anybody in this room that climate change is one of the most pressing challenges of our global society. And just to give you like an impression of what we do and how it's done. So I mean, in order to inform politics and decision makers, the climate scientists, they come together in globally coordinated experiments called, in this case, a CMIP. It's the couple model and a comparison project. It's been done in 2007, 2013, and 2021, and you can actually see that the amount of data which is actually used in these projects has steadily increased from just about 40 terabytes globally available for the first phase, well, in CMIP 3, up to about 11.2 petabytes being published and publicly available at the moment. So you can see that the data amounts are really increasing by a lot, and that's just the current state. So in the end, CMIP 6 is currently the data set which is actually used by politics and decision makers to inform decisions. Now that's today, and the state was digital twins. So actually, I can pick up on the topic of Sharif's talk here, is that there's an initiative it's called Destination Earth, Destiny, where there is a digital twin of the Earth system planned, and I can just tell you, of course, that this is an upcoming global effort which is really putting infrastructure of the global climate science community to the test. It's going to be exabytes of data, and it's going to have to be accessed by everybody essentially who works on climate science. So the point is, this is a challenge, and FDOs are going to be able to help us here. And it's about the ever-increasing complexity of the models, the data amounts, and the diversity of the data usage of climate data, which which it needs for an efficient and economic resources to be just more efficient and to save especially money and human resources. Because in the end, it's about the brain power, which is actually wasted if we don't have an efficient system. So that's kind of the approach where we have to go. Now, I've got like a little wish list here. So like, what would we actually need in order for Earth system modeling workflows? You run climate models on a supercomputer. So we have to have an efficient access and to-end discovery and processing of the very large local and external data sets. Plus, it would be very good to have an end-to-end solution for the entire workflows, including an automated output and data handling. For example, it would be nice if you have a system to get the model runs set up and running on the HPC. It would be very good to have your simulation actually being coupled to a workflow system where the data gets automatically ingested into catalogs. You would have to have a stock of reusable scripts and processings and all these kind of things. And in the end, it would be good to have a entire data package in accordance with the FAIR principles. For example, if you want to publish data and have your workflows being reused. So we're talking about data is there, but how can we actually make use of the entire package? The good thing is that climate science has a big heritage of global data sharing. So as I'm saying on the very first slide, data has been globally shared for the past about 20 or so years, and this has been done especially in the SGF. It's a system federation. It's a global federation of data nodes, where actually nowadays data is open accessible actually by anybody. And good thing is that in terms of FDOs, I think with the climate science community, it's actually gone a good way forward. So the data which is available in the SGF is very highly standardized. So there have been, the decades of discussion in the communities actually agreeing on standards, and it's been a long discussion. So I think this whole FDO concept of having to agree on a common standard, it's going to take a long time, but I think I'm very optimistic that it's going to work out. The data which we have is the machine actionable, good file formats. The PADs are provided actually at the level of the files. So we're talking, I think we're on the order of millions. So it's a lot of PADs which are already there. Plus we also have PAD kernel information, at least for CMAP 6. So actually we're quite ready. But so the data is prepared in a good way, but we have to go further. So we have to have an infrastructure for the workflows to get the big picture. And I'm just going to present what we have at DKZ. So a tool which we have at DKZ is called FREVA. FREVA is a software infrastructure which is built to work on standardized data and tool solutions, especially on HPC systems. It actually runs on the DKZ machines, and it can the customers or the scientists can have actually customizable software plugins to work with the data. So there's a paper out there, there's a link down there, and you can have a look at the DKZ at home pages. So specifics. So actually, to do it in an FDO framework, what can FREVA do now, and what do we still have to do? So what I can do now is that FREVA works. It's a web interface system. It's got a database which is fulfilled by actually exploiting the domain-specific standards for metadata. and it actually can access the database at the AKZ, so the file system, plus it can also get access to external sources. It can have user-defined workflows, which you can do like, you can look at data, process data, and publish data, and visualize it. The provenance of every workflow which is performed is being documented in the internal level. Plus, the system also assigns PIDs in the internal database to actually every data product which is created along the way. Now, this also this sounds very nice, but to go further even, so what's the further development of FREVA, especially in the context of FDOs and the complete workflow projects, we have funded projects actually, so there is money involved actually, so actually we're happy about that. So in the Warm World project, which actually Amirpasha is involved as well, we're going to be developing this end-to-end model workflow to start the model in the interface, run it on the HPC system, schedule it with a Slurm schedule, and then have the entire data stream in database, plus cataloging of the simulation and the output data. And then the big goal in this in the project these ways of phase 3, we plan to really go towards developing a domain-specific FDO standard, which builds on the, of course, still to be, well, conceived, as I understand it, a general FDO concept for everybody. So kind of, in my view, the FDO concept is like there's a general framework for everybody, plus domain-specific, say, extensions, and that's kind of in the proposal, in the wording, and I think it's going to be funded. So there's actually FDO work going to be funded, plus yeah, then kind of being able to actually also have the workflows in FREVA be FDOs themselves. So actually having all the information which you need for the workflow within PIDs, information, so that anybody in the future can theoretically repeat a workflow which was done to achieve a certain model result. So it's kind of in the future, but it goes towards this question of data archiving. What do you save? What can you save? What can't you save? So the direction which we're going is to being able to repeat the workflow and not save the data, because data is just too big. So it's kind of the overall goal. And thanks for that. I'm done. Thank you. There you go.
So many of the talks have workflows defined by PIDs. It's really good. I think one of the things that the community has to grasp is that not only software or data need PIDs. Sorry, I keep doing that. I'm the only one using the mic, but I'm telling everybody else to go to a mic, right? So there was no question there, just general happiness to see that workflows are being fully described by PIDs and workflows so they can be reused.
Very nice story. Nice to hear that. I have a question. Since you are talking about exabytes, and what we are trying to accommodate in the healthcare sector is data visiting, because that's about privacy, but that's not your concern. But if you have that FDOs, is it then possible to visit, or is it the intention to visit the data, or do you still copy the data to certain analyze environments?
That's a very good question. Of course, with data coming in scales of exabyte, it's going to be impossible to really transfer data on big scales. It's just not yeah, it's just not going to be doable. So we're going to have to work on solutions to have a federation of, say, databases where you can have a data query on a local, well, on this server, so so that the data is going to be processed close to where the data actually is. But of course, the point is also, if you look at these big supercomputers, so there was a mention of the system in Finland called Lumi. So the disk space on Lumi is not really it's not that large if you compare to the overall HPC performance. So the point is, if you do a simulation, for example, a climate run on Lumi, it's going to be far too large to be stored on that computer for a long time. So we're going to have to think about solutions on how to get data from the big HPC clusters to centers where there's more storage space. Well, for example, DKZ, like in Hamburg, we've got like at the moment we have 120 petabyte disk space. If you go for Lumi, I think it's about 100 or so, or well, it's a much a stronger machine, but with a comparably smaller disk space. So we have to kind of, get at solutions on how to best get this data streaming, data and transfer processing. It's going to be a big problem. I totally agree.
Yeah, thank you very much for the talk. When you talk about saving the workflows, of course, because there's too much data, so I'm wondering how far down the level of the computing stack you actually need to save, and is the goal still reusable or reproducible results, because of the architecture is changing very often, and the lack of deterministic results that we can get on parallel architectures. Thanks.
Yeah, that's a very good question, and that's a question which we think about actually all the time. So we don't know yet, actually. It's we don't know yet. I mean, of course you can save the scripts, you can save the compiler options, you can save the environment, you can kind of, I don't know, do a Docker, but it's not going to work. It's impossible to have a real reproducibility of a certain model simulation, and then you ask the question of what actually is reproducibility, and what does it actually mean in certain scientific fields. I don't know yet. It's a big discussion. So in my view, if you do a model run again and you get the same statistical results in the end, by I don't know, it's fine in my view. But if you have a simulation, for example, of a big run, and there's a storm right there, and if you do the run again, the storm might be gone because of a bit flip. So it's a very tough question, and I still don't know the answer, and it's active research. Yeah.
So I'll let you maybe talk with him directly as we. Everybody's been very, very on time throughout this, so I'd like to thank all the speakers for making this very easy logistically to not only bringing engaging content, but also keeping on time. So thanks, everybody. I think it's lunchtime, and I'll let you talk individually after this. Thank you.